Start recording. Okay. So we have discussed symmetry in quantum mechanics, and we define the symmetry as a unitary operator U, which acts on the state vectors, transforming them in another state vectors, and which was acting also on operators. Sorry, the pen doesn't work. Okay. On operators, transforming them in another operators. And in quantum mechanics, we define the symmetry as such operator which leaves the Hamiltonian invariant, or stated conversely, the theory was symmetric with respect to the symmetry described by operator U, provided the Hamiltonian was invariant with respect to the symmetry. This is the case of the quantum mechanics, where the Hamiltonian as a generator of time translation, so to say, and time, which is the evolution operator, evolution parameter in quantum mechanics, play an exclusive role in some sense. But in the case of relativity, you know that time is mixed with coordinates during the Lorentz transformation, and also the energy is a member zeroth component of the 4-vector of energy momentum, and it also mixes under the Lorentz transformation. So this definition of symmetry should be in some sense reformulated in the case of relativistic quantum field theory. We will return to this issue later, but the basic feature of the symmetry, that means we have some group which is mostly the Lie group, and this group is represented on Hilbert space by unitary or anti-unitary operators. This concept is preserved also in relativistic quantum physics. So in order to make these statements more precise, we would have to recapitulate some basic facts about the Lorentz group. So, you probably know the definition of the Lorentz group. Suppose that we have two space-time events. That means space-time event with coordinates t and x, and other event with, say, t primed and x primed. And the Lorentz transformation is defined as the most general linear transformation which preserves the interval between these two events. That means the interval defined as t minus t primed squared minus x primed squared is invariant. Of course, in the case when this invariant is 0, we can interpret this equation with, say, t and x fixed as an equation describing the wavefront of the light emitted.
To interrupt you, but
yes,
there may be a person
squared
in the waiting room.
Squared, yes. Thank you. So, in the case when s equals to 0, this is nothing else but the equation for the wavefront of the light which is emitted, say, from the point t primed, when we fix t primed and x primed, and which corresponds to the propagation of the light from point-like source and emitted from the point t primed and x primed. And in fact, this invariant is therefore responsible for the fact that the light travels in all inertial frames by the same speed. In fact, this definition in terms of interval can be rephrased as a definition in terms of invariance of the scale product, since if you have two such events, tx, t prime, x primed, and say t, I add some index here, tx, tx, ty and y, and ty primed and y primed, and let us define delta x as tx minus tx prime x minus x prime, and similarly delta y as dy minus dy primed, y minus y primed. It is an easy exercise, and you will probably do it during the seminar, that provided delta x squared, which is just this tx minus tx primed minus x primed, is conserved. That means if this is invariant, then also delta x times delta y, which is nothing else but tx minus tx primed down ty minus ty primed minus x primed and minus y primed, scale product, is invariant. The definition in terms of such a scale product and definition as which should be invariant, and definition with respect to this interval, which should be invariant, are equivalent. So the most general linear transformation of the coordinates in the space-time, let us write x mu, just this t and x, can be written in the form of x prime, this is the transformed coordinate, is given by, index should be upper index. There is some matrix, lambda mu x mu plus some constant vector a mu. This is the most general linear transformation, and we see that provided we introduce the space-time metric, the Minkowski metric, as diagonal matrix 1, minus 1, minus 1, minus 1, we can write this scale product delta x times delta y as eta mu mu delta x mu delta y mu, with obvious definitions what these components of delta x and delta y are. If we insert the definition of primed, transformed x and transformed y, we demand that delta x primed mu times delta x primed y is preserved. We obtain the following condition for this matrix lambda mu mu. Simply we get the delta x prime mu is lambda mu mu delta x mu, and from this we obtain lambda mu mu lambda alpha beta delta x mu delta x delta y beta should be eta mu eta alpha mu beta should be eta mu times delta x mu delta y mu. And this equation should be valid for any delta x and delta y. So we get the following condition comparing coefficients of delta x, delta y in the form eta, say, mu beta lambda mu mu lambda. I missed some indices here. There should be, of course, alpha. And doesn't work again. So here should be again alpha, lambda, alpha, beta should be eta mu beta. We can rename this index here as beta, and then we obtain this formula. This formula can be interpreted as the invariance of the Minkowski metric with respect to the Lorentz transformation if we understand the transformation of the metric as a tensor, and these indices are transformed in the same way as the indices of delta x or delta y. So this is the definition of the Lorentz group, and now we can try to find some consequences of such a definition. So the first thing is that we can easily rewrite this equation in matrix form. If we define the matrix eta alpha beta, as I already have written, as diagonal 1, minus 1, minus 1, minus 1, and we define this will be matrix eta without indices, and if we define matrix lambda mu nu without indices as lambda with, say, row index and column index, we see that this contraction here is the row times column, so we can write it as eta times lambda, and this contraction is contraction of row times row. That means it's contraction of lambda transpose times eta. And on the right hand side, we reproduce the eta. So this is the matrix form of our condition. From this, we can obtain one very useful equation, and this is equation for the inverse of the matrix lambda. We see that the matrix obeys the equation eta squared equals to 1. So if we multiply both sides of this equation by eta from the left and with lambda to minus 1 from the right, we obtain that eta times lambda transpose times eta is nothing else but lambda inverse. So this is a very useful formula for the inverse matrix, and we can interpret this also in indices. We can introduce also the eta with indices mu nu as upper indices, again as diagonal matrix 1, minus 1, minus 1, minus 1. And we can rewrite then this expression as lambda inverse mu nu as lambda transpose eta times eta, but one of these eta should correspond to upper indices, and the second eta would correspond to the lower indices. So we can write it in the form eta mu alpha lambda beta alpha eta beta mu. You see that the fact that this matrix lambda is transposed is that instead of contracting here column index with row index here, we contract here column index with row index, and here we contract the row index with column index. So this can be interpreted as a lowering of this beta index. This was our definition of lowering of indices. Simply, if we have some upper index, we can lower it just by this metric. And vice versa, here this lower index alpha is getting upper by this eta mu alpha. Again, if we have some object with lower index, we can change the position of the index with Minkowski metric. So this is nothing else but lambda nu, and fine. What can we say about the topological structure of this Lorentz group? First, the defining condition lambda alpha beta lambda alpha mu lambda beta mu is eta mu nu. In fact, means that if we fix this index mu and this index nu, we see that we fixed the column index, and that means that the columns of the matrix lambda are orthogonal in the sense that if we take mu equals to 0, we get the following equation: eta alpha beta lambda alpha 0 lambda beta 0, which can be rewritten as lambda 0 0 squared minus lambda 0 I lambda 0 I, and this should be eta 0 0, and this is 1. So we have normalization of the 0th column of the matrix lambda. Analogously, if we take both the indices mu and nu as space indices ij, we get similarly lambda I lambda j, this is the column index, and 0 0 corresponds to the first term of this sum over upper indices minus lambda k a lambda k j, here is summation of this k assumed, and on the right hand side we get eta ij, and according to a definition of this metric, this is nothing else but minus delta ij. And finally, if we take mu 0 and nu space index, we get lambda 0 I lambda 0 0 lambda 0 I minus lambda again contract over the k index 0 I, and this should be eta 0 I, and this is 0. So we can interpret this equation as scale product of the columns of the matrix lambda, and this means that these columns are orthogonal. You see this delta ij and this 0, and normalized. That means the indices with 0, the column with 0 column index has positive norm, and the indices, the columns with space indices have negative. This defining equation allows us also to determine the number of free parameters of the Lorentz group. We see that there are together 4 diagonal relations of this type when index mu and index nu is quill, and 4/2 binomial combination of different indices mu and nu. We simply choose 2 elements from 4 possible elements, 4 possible indices. So together we get 10 parameters. But the general Lorentz transformation x mu prime is lambda mu nu x nu plus a mu contains also 4 independent parameters a mu. So together we have 10 plus 4 parameters of so-called inhomogeneous Lorentz group. Inhomogeneous Lorentz group is Lorentz group of such a transformation, including this space-time shift described by this parameter alpha mu. When we assign to each such a transformation the double, simply the matrix lambda mu nu, and the parameter a, we can find the composition rule for such objects. Simply, if we do 2 transformations, lambda 1 and lambda, describe lambda 1 and I1, and compose it with other transformation, lambda 2 and A2, we get result which looks like lambda 1 times lambda 2 and A1 plus lambda 1 A2. We can also get identity transformation if here is unit matrix and A is equal to 0 of this is the unit element of our inhomogeneous Lorentz group, and we can also obtain inverse element, and this inverse element is lambda inverse and minus a lambda inverse times A. It is easy exercise to prove all these equations, And you will probably do it during the seminar. So this is an exercise for you. Of course, you can easily prove that such a composition rule is associative. And as we have seen, the inverse element of any lambda, which is in the Lorentz, exists. This lambda to the -1 is given by this operation. So it is these doubles, matrix lambda and shift A, form together a group, and this group, as I have already said, is just what we call the inhomogeneous Lorentz group. This group have distinguished subgroups, and these subgroups correspond to so-called homogeneous Lorentz group. These correspond to the double lambda and A equals to 0. This group is sometimes called also L, or orthogonal group 1, 3, 1, 3, because our metric eta, which is preserved by the transformation of this group, in the sense I have explained before, in the sense of this equation, has the signature 1 minus and 3 plus, 1 plus, 3 minus. There is also a subgroup which corresponds to space-time translations, and this is given by doubles 1, unit matrix, and A. Of course, if we use this composition rule, we easily see that such doubles form an abelian group, since 1 A1 times 1 A2. If we use this composition, we get product of these two matrices. This is again 1 and A1 plus lambda 1. This is 1 times A2. And this is just the composition rule for abelian groups. Of course, it is trivial in some sense, because the space-time translation are obviously independent on the order of these operations. What is a little bit less obvious is that these translations, we call it T4, the group of translations is normal subgroup of inhomogeneous Lorentz group. You will probably prove this as an easy exercise during the seminar. So, how can we say something about the topological structure of the Lorentz on the homogeneous Lorentz group, that means of O1, 3. Our definition of matrices lambda was eta times lambda transpose times eta, is eta, or we can rewrite this as lambda transpose times eta times lambda. If we multiply it by lambda from the right.
Excuse me, but eta times lambda transpose times eta should be lambda to the -1.
Sorry, it's of course nonsense. Our definition was the following. Sorry. Lambda t times lambda is eta. And if we take determinant of this equation, we obtain on one side determinant lambda t times determinant eta times determinant lambda, which is nothing else but, since we know the determinant lambda is the product of diagonal elements of this, is -1. And the determinant of the transpose matrix is the same as determinant of the original matrix. So we obtain minus determinant squared of lambda. And on the other side, we get -1. So we see that we have the following condition for these matrices lambda in the homogeneous Lorentz group. Determinant lambda squared is 1. That means that determinant lambda can be either plus or -1. Of course, the matrices with determinant lambda plus, for the matrices lambdas with determinant lambda equals to +1, we simply get that this is a subgroup of the homogeneous Lorentz group. Simply determinant lambda times, sorry, I'm not able to switch, lambda times lambda primed is determinant lambda times determinant lambda primed, and provided both these lambda and lambda primed have positive determinant, again their product has positive determinant. So we have one distinguished subgroup of homogeneous Lorentz group, and this subgroup is called the proper Lorentz subgroup, and it is usually denoted as L+. Of course, because this is subgroup and it is the component of the Lorentz group, which includes the unity of the Lorentz group. And this L+ is sometimes called special orthogonal group 1, 3. Special because the determinant is equals to 1. We can also return back to these equations, the defining equations written in components, and we will be concentrated on this one. We see that if we rewrite this, we can write it in the form of lambda 0, 0 squared, and this term we will write on the right hand side. So is 1 plus lambda 0 I, lambda 0 I, here we sum over these i's, and of course this is positive or 0. So we see that lambda 0, 0 squared is greater or equal to 1, and this implies, and this implies that lambda 0, 0 is either larger or equal to 1 or smaller or equal to -1. So we see that our Lorentz group O13 is decomposed into 4 connected components. The first is denoted as L plus and such an arrow upwards, which is a subgroup and which includes unit of the group. And this is determined by the condition determinant of lambda is 1 and the lambda element of the matrix lambda is greater or equal 1. Of course, you will probably see that this is really a subgroup, and this is again leave to exercises. The second component is the component which doesn't correspond to any subgroup, but which includes so-called parity operator or space inversion operator. This space inversion operator is a diagonal matrix of the form 1, -1, -1, and -1. And this have determinant negative and lambda 0, 0 positive. Other component is the component with, say, positive determinant and lambda 0, 0 negative. And this contains so-called PT operator. This is a space-time inversion. PT is a matrix which is diagonal and -1, -1, -1, and -1. So it has determinant positive, but the lambda 0, 0 element is negative. And finally, we get such a subgroup, minus and row downwards. And this contains so-called time inversion operator. And this time inversion operator is diagonal of -1, 1, 1, 1. Here the determinant is negative, and lambda 0, 0 is again negative. These connected components cannot be, or the elements of these connected components cannot be connected to each other with a continuous curve which interpolates continuously between the elements of the group. That means if we have some lambda, say from plus minus, all these elements lambda can be connected with the unit element of the group by continuous path. That means by some curve in the group space. But if we have, say, lambda from lambda plus upwards and lambda primed from lambda minus.
Někdo je ještě ve waiting room, jestli byste ho mohl pustit.
Sorry. Okay. Fine. So provided we have two elements from these components of the Lorentz group, there doesn't exist a continuous path connecting them. Sorry. Since provided this path is connected, also along this path the determinant of lambda should be continuous. And provided this path is continuous, the determinant lambda is continuous, but here we have lambda plus 1, and here we have determinant lambda minus 1, and we cannot simply jump from discrete value plus 1 to discrete value minus 1. And analogous situation is between the other components of the Lorentz group. On the other hand, we can say something about the structure of the matrices from these components, because every component lambda from, say, L minus upwards can be written as this distinguished P operator times some element lambda primed from the subgroup L plus upwards. By the way, I forgot to say that the elements of the group with lambda 0, 0 greater than or equal than 1 from subgroup. And this subgroup is called orthochronous Lorentz group and is denoted with this arrow upwards. This group, subgroup lambda plus and arrow directing upwards, is called orthochronous, proper orthochronous Lorentz group. Sorry. And similarly, if we have lambda from this lambda plus, we can write it again as PT, this distinguished PT operator, times some lambda primed. Well, again, lambda primed is element of the proper orthochronous Lorentz group. And of course, again, in the case of lambda from L downwards minus, can be written as T operator, the time inversion operator, times some transformation lambda primed from proper orthochronous Lorentz group. So we have several subgroups of the Lorentz group. We have subgroup SO13, or the proper Lorentz group. And we know now that this subgroup is not connected. It has two components, and these components are just this one and this one, this one and this one. And again, the subgroup corresponding to orthochronous Lorentz transformation, that means those which do not change the sign of the time component, is again a subgroup which is not connected, and it corresponds to this one component and this one component. Let us discuss some special subgroups of the Lorentz group which are other from these. The first distinguished subgroup is the group of rotations, which can be written as block diagonal matrix, where here is some 3 times 3 matrix. We know that the definition of the Lorentz group is just lambda t Let us denote this. Let us denote this as as lambda r. If we use the definition of the Lorentz group, we get lambda tr times eta times lambda r should be eta, which written in this block diagonal form is nothing else but 1, 0, 0, and this R matrix transpose times our metric tensor times 1, 0, 0, r, and this should be just 1 minus 1 in this block diagonal notation. And if we do this matrix multiplication, we get 1, 0, 0, and here we combine this R transpose with R, but with minus sign here, minus RT, RTR. And this should be 1, 0, 0, minus 1. So from the definition of the elements of the Lorentz group, we see that we get the following constraint of this matrix. This is the 3R3 matrix. And this is nothing else than definition of the rotational group O3. So this rotational group is subgroup of our homogeneous Lorentz group. And if we prescribe determinant of R equal to 1, which corresponds to the SO3, we see this SO3 is a subgroup of SO13. That means the proper Lorentz group. Let us remind you some example of such a rotation. Typical example is, for instance, the rotation along the third axis with some angle phi, and this can be written in the form of cosine phi, sine phi, 0, minus sine phi, 0, and 0, 0, 1. It is easy to see that such a rotation form one parametrical subgroup. This is an easy exercise, I can leave it to seminar, to show that if we take R3 phi times R3 phi primed, we get R3 phi plus phi primed. So this one parametric group is an abelian group. Another example of Lorentz transformations is less trivial. It is the case of boosts. So we are interested in the boost in the third direction. We will call it B3. And we introduce some parameter u. I will explain you later what it is. You know that such a boost can be written if can be parameterized by the relative velocity of two inertial systems, and we get such a transformation. And x prime 3 gamma times x3 minus v times x0. So here this gamma is the Lorentz gamma factor, as you know, and the corresponding matrix B3 can be right off from these formulas. Simply we get gamma 0, 0 minus gamma v from the transformation of x0, 0, 1, 0, 0 from the transformation of x1, 0, 0, 1, and 0 from the transformation of x2, and finally minus gamma v, 0, 0, gamma from the transformation of x3. And this can be parameterized in another way, simply using the parameter which is known as rapidity. This rapidity is defined as 1/2 of logarithm of the ratio 1 plus v minus 1 minus v. And if you use this definition, you can rewrite these Lorentz factors and this gamma v in terms of functions of this u, and the result looks in some sense similarly to the case of the rotation, but we should replace the cosine and sine by hyperbolic cosine and sine. So we get cosine hyperbolic u 0, 0 minus sine hyperbolic u 0, 1, 0, 0, 0, 0, 1, 0, and minus hyperbolic sine of u 0, 0, and hyperbolic cosine of u. Again, these boosts along the third axis form one parametric group, and this group is abelian, of course. And the composition rule of this group is simple if expressed in terms of the rapidity. If we compose two boosts with parameters u and u primed, we get as a result, again, boost along the third axis with rapidity, which is sum of the rapidities of the individual boosts. It is instructive to see this in somewhat different context. We can rewrite such a boost along the third axis in terms of special coordinates on the space-time. Simply defining the coordinate, x plus minus as x0 plus minus x3, and the vector with two components x plus as free vector x1, x2, x1, x2, 0. And in terms of these coordinates, the boost B3u acts as x primed plus minus is nothing else but e2 minus plus u times x plus minus, and x primed is two-dimensional orthogonal vector to third axis is not changed. And from this you easily see the composition rule here. Since the Lorentz group acts on this x plus minus when we use boost on the third axis multiplicatively, and this multiplication leads to addition of the rapidities. This again is exercise. You probably can do it yourself, or you will do it during the seminar. Of course, we can generalize these concepts and introduce the boost in general direction, which is described by unit vector n, general unit vector n. Up to now, we use this n as the unit vector in the direction of the third axis. And we can use, of course, this to deduce how this transformation will be. Simply the component of the space vector x, which is parallel to the direction of the boost, will be transformed and mixed with the zeros component, while the two components which will be orthogonal to this direction of the boost will be unchanged. Then we can write this transformation as x0 primed is the Lorentz factor times x0 minus v times x. This automatically takes into account the component of x parallel to v. X parallel to v is transformed and mixes with the zeroth component, and the two components which are orthogonal to the direction of the boost are unchanged. We can obtain this x parallel projection of the vector x on the direction of v, so we can write it as v times x over v squared. And in terms of this unit vector, which tells us along which axis or along which direction we do the boost, it can be rewritten as n times x. And the orthogonal components is simply x minus x parallel, and this is nothing else but such an operator. 1 minus n times x, or we can write it n transpose in order to get this as matrices acting on this x. So putting this into a matrix, we get for a boost along the direction n with rapidity u. This rapidity is defined in the same way as before, using the absolute value of the velocity. Know that the velocity here is, of course, absolute value times the direction. We can write it as gamma here, minus gamma times the projector to the parallel component. That means n transpose. Sorry. We should get here this projection, so we should write here v times n. And if we would like to write it in matrix form, and if we suppose that the n is a column vector, this should be row, so there should be transpose. For the 3 times 1 column, we get here minus gamma v times n. It comes from this, and here we should take into account these two transformations. So the orthogonal part is not changed, so that the projection of the x to the directions which are orthogonal, the direction of the boost are unchanged, and the parallel part is contracted with this gamma, so plus gamma times the projection to the parallel direction. And this is this. So this is the boost along the direction n. And again, if we keep n fixed, these boosts along the fixed direction form abelian subgroup of the Lorentz group. And again, the composition rule looks like this. We can also rewrite the rotation along arbitrary action in the direction n and arbitrary angle phi in a matrix form. Again, here the x0 primed is, of course, x0. The component of x, which is parallel to the axis, is not changed. And the projection of x, which is orthogonal, is changed, is rotated, and we can write it as x, original x orthogonal, times cosine phi minus n times x times sine phi. Simply this orthogonal projection, and this second vector plays the role of the axis 1 and 2, which were orthogonal to the third axis, and these two independent orthogonal vectors, x orthogonal and this one, are just mixed by the rotation in the same way as the x1 and x2 were mixed by the rotation along the third axis. So this is nothing else but this matrix, cosine, cosine, sine phi, and minus sine phi, but written in terms of two orthogonal vectors to the direction of the rotation. So we can rewrite the general form of this rotation in components. The lambda r n phi 0 j component is, of course, 0 because the time is not transformed. Again, lambda r n phi say I 0 is 0 because the space and time doesn't mix by rotation, so this is 0. And what is interesting is the component with space indices, I, j, and here we get either the projection operator to the parallel direction to the axis. This is this one, and this doesn't change. And then the projector on the orthogonal direction. This is this x. This projects to this x orthogonal times cosine phi plus term which describes this vector product, and in components it is mk epsilon k ij times sine phi. So this is rotation along arbitrary axis by angle phi, and again if we fix n, we obtain again abelian one-parametric subgroup, and the corresponding composition rule is given by this prescription. Okay, so now we will also need to know what are the generators of the Lorentz group. And as you know, the generators of general Lie group tell us something about the behavior of the group near the unity of the group. Mainly, the generators correspond to the linear terms in the Taylor expansion of the groups near the unity. So we will be now interested in so-called infinitesimal Lorentz transformations. And these infinitesimal Lorentz transformations can be written in the following way. Here is the unity, which is represented by this conical delta, plus something small. In the case of inhomogeneous Lorentz group, we can also have infinitesimal space-time translations. And in such a case, we will denote the infinitesimal parameter of the translation as epsilon mu. Let us now rewrite the definition of the Lorentz group in terms of these infinitesimal Lorentz transformations, and let us keep only the terms of the first order in this omega mu nu. So we get eta mu nu should be eta alpha beta times delta alpha mu plus omega alpha mu times delta beta mu plus omega beta mu. And we get, of course, the first term corresponding to product of these two deltas. That means eta mu nu. And then we get the cross terms. The cross terms. And you see that the effect of these cross terms is simply, if we take product of this one and this one, we simply get lowering of this alpha index and renaming it as nu. So we get omega mu mu. Again, if we take the product of these two, it means the lowering of the beta index and then renaming as this index as mu, so plus omega mu mu, plus the terms which are of the higher order in this omega. So there should be identity at least to the, this should be identity at least to the first order in these omega parameters, and this tells us that this should vanish. Therefore, omega mu mu must be antisymmetric, omega mu mu. So we see that the infinitesimal Lorentz transformations are parameterized by antisymmetric tensor with two lower indices, and such a tensor has 6 independent components. This 6 is nothing else but the binomial 4 over 2, since we choose two distinguished index, two different indices from 4 possibilities. So we reproduce the number of parameters of the Lorentz group, and it seems that such a parameterization with respect using such antisymmetric tensor will be useful for us in what follows. Note that the infinitesimal Lorentz transformation lambda mu nu can be expressed also in a little bit different form. I will write it first and then I will explain you the symbols here. And here as a linear combination, this infinitesimal term will be written as a linear combination of some matrices which are indexed by alpha and beta and have matrix elements indexed by mu and nu. And these m alpha beta mu nu are the matrices which looks like this, minus I, this should compensate this I, eta mu alpha delta beta mu minus eta mu beta delta alpha mu. Simply, if you insert this definition of this matrix in this formula, you obtain identity in the sense that this equals what it should be, delta mu nu plus omega mu nu. And these matrices are very interesting because they play the role of generators of the Lorentz group. You see that the Lorentz element of the Lorentz group using these parameters omega alpha beta is a linear combination of some matrices, and these matrices are nothing else but the generators, as we had defined it in the previous lecture, of the defining representation of the Lorentz group. Because we know explicit form of these matrices, we can calculate some properties of them. Of course, as a function of the indices alpha beta, these matrices should be antisymmetric, since, as we know, these parameters omega alpha beta are antisymmetric. And we can also calculate the commutators of these matrices. And we get something like this: eta alpha nu m beta nu minus eta beta nu m alpha nu plus eta beta nu m alpha nu plus eta alpha nu m beta nu. This is a little bit of calculation, so leave it to exercises. But you can see that it is an easy way how to remember this formula. Simply, the first term is eta pairing these two first indices and m pairing these second indices. And the rest is constructed in the way that the expression is antisymmetric with both exchange of alpha beta and mu nu. So for instance, this term and this term differs by exchange of alpha beta. So there is minus sign in order to satisfy the antisymmetry, and so on. So it is necessary only remember this first term, and all the other terms can be simply derived from the requirement of antisymmetry in alpha beta and mu nu. Okay, so it's a good place to stop here. We have found that the generators of the Lorentz group in the defining representation obey some commutation relations. And in the same way, we, in fact, get also the structure functions of the Lorentz group as considered as Lie group. Okay, so I will stop here.